Does anybody know what one of these things are? A slide rule, that's right. You know how difficult it is to get one of these things these days. It's almost impossible. That's a slide rule. Yeah. And why is that important? Wait and see.
All right. Okay, 6 o'clock is arrived. Good evening, everyone. Lovely to see you all tonight on this wondrous spring thunderstormy day that we've had. Yes, thank you so much for making the effort to come along tonight in our next instalment of our public lecture series. Before I introduce Professor Harding, just a friendly reminder that you all turn off or put on silent your mobile phones as a courtesy to our guest speaker. And just to let you know that we do have emergency exits at the rear, at the sides, no fire alarm is scheduled. If it goes off, it's real. So rather than running around like headless chickens, we will just vacate the building safely via the main staircase and out into the physics car park. So without further ado, I shall introduce you to Professor Stephen Harding. Professor Harding, as you can see there, he's actually a professor of biochemistry, but when he was a PhD student, postdoctoral researcher, sorry, he was actually part of the research group of Dr. Creeth. And so he's able to speak with very good and very real experience of working alongside this great man. So without further ado, I'll hand over to Professor Harding. Thank you so much for tonight's talk.
Thanks, Sam. And it's a great honour to be invited by your team and the British Science Association. And it's good you've come, actually. I mean, I had thought, gosh, you know, DNA, National DNA Day was right in the middle of the vacation here, also Easter week. And I had thought about ringing up the organisers of National DNA Day, I think in America, to see if they could change it. So it was outside Easter week and in term time, and they politely refused. That wasn't true, of course. I didn't approach them. So thinking we get about 6 people, it's great that we've got so many. And it's good because not many people know this, but Nottingham played a very, very big role in the discovery of the double helix, which Watson and Crick deservedly get most of the credit for. Also, Rosalind Franklin and Maurice Wilkins, they're now getting the credit that they have deserved. But Nottingham played no mean part in that discovery, which is arguably the most important discovery in biology, at least, of the last century. And if you talk to people, have they heard of Creeth, Gulland, Jordan, these sort of people in the discovery of DNA? And most people have never heard of them. Even in Nottingham, still, people aren't familiar with what the contribution that we made. So I thought this was a great chance to help to put the record straight. So I bit Sam's hand off when she asked if he wanted to give a talk on this stuff, and we targeted National DNA Day. And National DNA Day is so called because on this day, way back in 1953, a series of 3 papers were published describing the structure of DNA. One was, of course, the Crick-Watson paper describing the double helix structure, this drawing by Audley Crick, but also back-to-back papers by Maurice Wilkins and his research associates, and also Rosalind Franklin and Raymond Gosling, both describing X-ray work, including the famous photograph 51 of Rosalind Franklin, which proved crucial to the elucidation of the DNA double helical model of Watson and Crick. So those papers appeared back-to-back on this day back in 1953. And here's this famous picture of Crick and Watson. And Francis Crick has in his hand the famous slide rule. pointing out an important feature in the DNA molecule, which might be hydrogen bonds. I'm not sure. I need to look at that more carefully. Now I'm going to show a couple of clips from a film that was made in 1987 with Jeff Goldblum playing Jim Watson and Tim Pigott-Smith playing Francis Crick. And it's two bits near the end. The first one is where Watson gets the base pairs right, or thanks to the intervention of Jerry O'Donoghue, who points out the correct tautomeric forms of the bases he should be using. And the final one is of the DNA structure itself. Yeah, so that's a bit where they get the model finally sorted. And that was a crucial moment because even at that time, 1950s, people were still doubting that nucleic acids were held the code, the genetic code for life. People thought the variation was too small to allow for that in the composition. People still believed that proteins may hold the code for genes. And this was the defining moment. And the double helical structure provided the mechanism for replication. And on this tiny model here, sorry if you can't see this, but you've got the sugar phosphate backbone on the outside with the phosphates in purple and the sugar rings in red, the deoxyribose. And then the base pairs, known as these plates running through the molecule. But crucial were the bonds which hold the bases together, the hydrogen bonds shown in white here. And the key thing about these hydrogen bonds is in this sort of quasi-space-filling model here, although the other bonds are rigid, the hydrogen bonds are still strong, but not so strong that they can come apart and reform. And that proved crucial in the model. I just start out of that. Okay, this is that drawing of Crick again. And because these bases could be not too difficult taken apart and reformed again, that provided the basis for replication. So hydrogen bonds were very important in this model. And in that first clip, we heard that Watson was able to get the bases to form these hydrogen bonds once the correct tautomeric forms were obtained. And people have been working on the incorrect enol form before, and the tautomeric forms depends on the position of the hydrogen atoms either on the oxygen or on particular nitrogens. So this is the enol form of thymine with the hydrogen on this oxygen here, and the keto form is on this nitrogen here. And with guanine, again, the enol form is with this hydrogen on the oxygen, forming a hydroxyl group, and with the keto form, it's forming this amine here. So once that was sorted, the base pairs could be sorted. And this is a diagram from Watson's book, the famous double helix book. There's a new edition of this book now called the New Illustrated Double Helix, which is very, very interesting. But we'll come back to that later. So these are these hydrogen bonds being formed between the bases. And originally they had two bonds for the adenine thymine and two bonds for the guanine cytosine. But it was later realised there should be a third bond between G and C. Right. So that was what was discovered in 1953. So it was Watson and Crick's model building using essentially X-ray data of others, principally Rosalind Franklin and Maurice Wilkins. But that's not the entire story. The discovery of the double helix, the secret of life, involved many other people going back right until the 19th century. And this is not everybody who's been involved with the DNA discovery. I've just highlighted some of the people, some of the key people here. And we start off with Misha in Germany in 1869. He discovered a new type of molecule called nuclein, or nucleic acid, from white blood cells. He found that the normal processes of isolation of and purification used for proteins didn't work, and a new method was used to produce a different type of molecule, which he called nuclein, and which later became known as nucleic acids. So this was the first isolation, if you like, of DNA. And then, if we go further, this is Phobos Levine, and he did some great work because he identified the components of DNA, and he came up with this structure for a DNA chain, which is basically a sugar phosphate backbone. The sugars, these deoxyribose sugars, linked by these phosphate residues, and with these bases attached to carbon atom number 1. And that was great. There's a saying, you should quit while you're ahead, and unfortunately Levine didn't. He took a step further, and he said that the bases were alternating, pyrimidine and purine. Pyrimidine bases, thymine and cytosine, with a single ring structure, and the purines, adenine and guanine, with the double ring structure. So he had this hypothesis, which almost became universally accepted, that you had this alternating structure based on the findings from DNA from different sources, that the molar ratios of C, T, A and G were approximately the same. And that meant there wasn't that much variation within the DNA molecules, and fueled the belief that it was really proteins with all different amino acids and all different combinations you could get with those, which really held the genetic code, and not the nucleic acids. Nucleic acids were considered perhaps as a store for phosphorus in the cells by many people. So his hypothesis put the clock back in a way, whereas things were developing nicely. So I think we'll leave it there for Levine's. And this was quite a major discovery, this linear polymer of this sugar phosphate backbone with the bases, these nucleotides. Yeah. And then Florence Bell and William Asprey. People think of, well, X-ray diffraction, that's Rosalind Franklin, but actually there was another woman involved 10, 12 years before that. That was Florence Bell at Leeds, who was a PhD student, and Asprey was her supervisor. And they came up with their own diffraction patterns on not very pure DNA material. Purity was very, very important, as we'll see later on. But on these not very pure DNA samples, you can see just about resolvable some features in this diffraction pattern. nothing like the quality that Rosalind Franklin was able to produce, the famous photograph 51, which Watson and Crick used, but on much higher purity DNA. But nonetheless, with this rather impure DNA, they still were able to make some important conclusions about the DNA molecule, and in particular about the regular stacking of the bases, which were perpendicular to the backbone, and they also work out the spacing of 3.34 angstroms. So this was a remarkable step forward. And that was coupled with experiments on cells, which were starting to point towards nucleic acids as the molecules where the genes were. And work by Avery and also Pollister. And Pollister in New York used this ultraviolet microspectrophotometer device, which is able to quantify the amount of DNA in cells. What he showed was DNA in all cells in an organism was constant, except for the sex cells, which had 50% less. Then the DNA content doubled shortly before cells divided. So this strongly pointed to the fact that DNA and not protein that played the genetic role in cells. Right, so that was the 40s, and then there was this, 1947, with the publication of 3 papers in the Journal of the Chemical Society describing the discovery of hydrogen bonds between the bases. And this, of course, proved crucial later with the Watson and Crick discovery. And the team consisted of these guys here, Gulland and Jordan, and these PhD students, Creeth, Threlfall, and Taylor. Now, Gulland was a remarkable man. He was an FRS, and he joined not University of Nottingham, it was then called University College Nottingham. It was before the university got its royal charter, which was 13 years later. So 1936 he was appointed as Jesse Boot Professor of Chemistry. And not long after that, he appointed Dennis Jordan, or we call him Dodge Jordan, everyone called him Dodge Jordan, as his research assistant. Hadn't got a PhD, but Dodge registered for a PhD part-time, working on the physical chemistry of nucleic acids. So Masson, with Jordan, set up the nucleic acid laboratories in the old chemistry department in University College Nottingham. And then when Dodge got his PhD in 1944, he was joined by his own PhD student, which was Mike Creeth, who was jointly supervised by Dodge and by Gulland. So Dodge was the day-to-day supervisor, and Gulland was the overall supervisor. And Gulland was regarded as one of the leading nucleic acid chemists, if not the leading nucleic acid chemists, maybe with Todd in Oxford at the time. So he was very highly respected. So it was quite a coup getting Masson here and in this team being formed. And where were the laboratories? Well, we'll come to that at the end of the talk, because that's an interesting story in its own right. But they were in the Trent building, the old Trent building. So, and in the northwest corner of the Trent building, which sticks out right at the back, that's where these laboratories were. And it's quite interesting now because, of course, chemistry has long since moved from the Trent building. But now, where the chemistry labs used to be, which is on the first floor of the Trent. It's now part of the Spanish, Portuguese, and Latin American studies. You know how times have changed, and it was quite moving actually, standing in this area where my old boss Creeth was all those years ago, doing all those experiments on DNA. But I'll come back to that at the end, because there's a nice sort of ironic twist about all this. So these are the 3 papers that were published in the Journal of the Chemical Society. And the first one, by Gulland, Jordan, and Threlfall, described the production of high-quality, very pure, high molecular weight DNA. And this was Gulland. Gulland was always banging on the drum, saying how important it was to have preparations of material which are the highest quality, particularly with nucleic acids. He argued that experiments on improperly purified material were or can be less than useful. So the first part of the program was in the production of high quality DNA and avoiding procedures which would compromise that structure. The application of high acid or high alkali to remove proteins. Other methods were used to do that, which were non-disruptive. And it was successful. And to check on the purity, so these are similar materials that were produced from Uppsala in Sweden, using a procedure very similar to what Gulland was using. And this material was used by the team at King's College to get the high-quality X-ray measurements. So working on high-purity calf thymus DNA. Now, how do they check the purity? Well, those that know me know that I have to bring this technique in, and it's the analytical centrifuge. And this is quite a new technique then. Svedberg got the Nobel Prize for it not long before. And this was the Svedberg oil turbine analytical centrifuge. And what a centrifuge is that it's a very high speed machine, for creating high G-forces so you could sediment very small particles like DNA, like proteins, and like sugar polymer types of molecules. So these very high G-forces in these centrifuges are ultra, that means very, very high speed centrifuges were necessary. And the analytical part means that as the material was sedimenting, you could analyse by special optics the sedimentation process and make deductions about the purity and size or molecular weight of the materials. Now, Gulland's team didn't go all the way to Uppsala in Sweden to do this. Thankfully, there was one of these Svedberg oil turbine centrifuge, so it hadn't really taken into account the discovery of electricity. Okay, that's one feature, but it worked beautifully. And this, by the way, is a photographic plate holder, so all the images were recorded on photographic plates. No computers or CD cameras in those days. But they had one of these at Oxford, in the laboratory of Sandy Ogston. So Gulland, Jordan and Threlfall passed their samples on to Ogston's team, Cecil and Ogston, to analyse, to check the purity. And if you can imagine, the direction of sedimentation is this direction here. So the G-force up to 200,000 G with these very high speed, 50,000 revolutions per minute. And this is what one of these rotors would have looked like, where the sample went went in, and the solution would go into these very, very high precision, what are called centrifuge cells with transparent windows so that the light could be passed through. And in doing this, you can see not the molecules, but you can see the boundary between the solution and the solvent left behind as the large molecules sediment. And straight away you can see this very sharp peak, which indicates a very highly pure material. And from the rate at which this boundary moves per unit centrifugal field, you get a parameter called the sedimentation coefficient. And that, combined with the diffusion coefficient, which you get from the spreading of the boundary with time, the sedimentation coefficient divided by the diffusion coefficient gives you the times a constant, gives you the molecular weight. So very high purity, and the molecular weights coming out were very high, just under 1,820,000. That means, yeah, the samples were good enough to analyse. And in fact, Cecil Logston published that paper the year after the papers from Nottingham were produced in the same journal, the Journal of the Chemical Society, the forerunner of the Faraday Society journal. Okay, so that was the first paper. The second paper involved titration of the highly purified DNA molecule, titration of the bases on the DNA. Now, I'm not going to go into this in great detail, but you start off with a neutral solution, and then you add quantities of alkali to basically titrate out the amino groups or amine groups on the bases, and then you go the reverse direction to titrate out the hydroxyl groups on the bases. Now, if we start off here and we start adding amounts of alkali, then the expected behaviour for the nucleotides is this. But what was observed was much different behaviour for the bases on the DNA. So something appeared to be blocking the amine groups. Something was stopping the amine groups from being titrated out. And similar behaviour was observed if you started adding acid. The expected behaviour was this, but this was what was observed. After very high alkali had been added or very high acid had been added, then normal behaviour had been resumed. So what the Gulland team supposed was that something was blocking these groups, and they thought it might be hydrogen bonds. So the DNA molecule was, the bases were hydrogen bonded, stopping the addition of, or reducing the ability of alkali and acid to titrate out the bases. And the final definitive study in this series of experiments was done by Creeth, Gulland and Jordan. And this involved a technique known as viscosity, combined with a related technique known as streaming birefringence. Now basically, solutions of DNA are very highly viscous. You see that sort of like syrupy consistency coming out? Obviously it depends on the concentration as well, but it also depends on the conformation of the molecule. So long rod-like molecules have a very high viscosity, or give solutions of very high viscosity compared to small, compact, say, protein types of molecule. So what they did was they measured the relative viscosity. That means the viscosity of the solution of DNA compared to the solvent, the buffer solution, or whatever the DNA solutions were dissolved in. So DNA has a very high relative viscosity, and they used viscometers, these special devices called viscometers, like this. This actually is a nice picture here of the viscometer. This viscometer belonged to Mike Creeth. This is one of his old viscometers. He didn't actually use this particular viscometer, but something quite like it. All these beautiful things. This is what science is about. Not about machines and pressing buttons and things, but by dealing with... and we're blessed here, actually, at Nottingham, because the chemistry department has still a superb glass blower who can produce and make devices like this. We've actually got him to make copies of this superbly, him and his assistants. So that was something which Creeth would have used, but also a slightly different one, which allowed variation in hydrostatic pressure. So these results here correspond to different hydrostatic pressures, and this difference indicates that the DNA molecules are what we call non-Newtonian. And that's a feature of elongated molecules which line up in response to shearing forces, giving a lower viscosity. So as you reduce the shearing forces, you get higher viscosity. That's the first clue, that we had a very long elongated molecule. The other clue was that if the molecules line up, then by shining light through the solution under viscous flow, you can observe a phenomenon called birefringence, which means material refracting light in different ways depending on the polarization of the light. And DNA solutions were very birefringent. So these are two pieces of evidence to suggest we had a very long molecule, in addition to the evidence that we get from the ultra centrifuge. And these results here correspond to material that have been treated with very strong acid or very strong alkali, with the structure essentially destroyed. So as you increase the alkali to high pHs, what they observed was that the viscosity dropped dramatically. And the same if they increased the acid, so that the pHs were very low, you get this dramatic drop in the viscosity, the relative viscosity. And the pH values at which this occurs corresponds almost exactly to what was observed in the titration experiments. So these were the definitive measurements which confirmed that it was hydrogen bonds that were being broken, and the structure was reducing to a much smaller molecule. So this was the definitive experiment confirming the existence of hydrogen bonds in DNA. This is the conclusion which they came to. They said that the critical pH values are coincident with those in which a liberation of amino and hydroxyl groups has been observed in the titration studies. And it's considered that the two phenomena are related and are due to the fission of the hydrogen bonds, postulated as linking the purine, pyrimidine, hydroxyl groups and some of the amino groups. This is the defining conclusion from those measurements. But then after those papers were published, Creeth wrote up his PhD, and then that became available. And Creeth's PhD which is now, you can get it online, it's now online with the British Library for all to see, is interesting for a number of reasons, but three particular reasons. First of all, if you look at the front, it says it's presented by James Michael Creeth, the degree of Doctor of Philosophy in the University of London. Yes. So, as I said, at the time they were doing these experiments, it wasn't University of Nottingham, it was University College Nottingham. So the degrees had to be ratified externally by University College London. Okay, the second interesting thing is in the bottom margin of page 85 is a structure for the DNA molecule. And I'll come back to that in a minute. But the third, which is very sad, really, if you read the acknowledgements, it says, my sincere thanks are due to the late Professor JM Gulland FRS for the continual encouragement and guidance he gave me up to the time of his death. So in between the time of the papers and Creeth submitting the PhD, Gulland had died. And that proved a disaster really for the whole Nottingham team. But to go back to the Creeth structure again, he's got this model based on the hydrogen bond discovery and based on the knowledge that the molecule must be very long. And so we've got this model of this two-chain structure with the sugar phosphate backbone on the outside and the bases on the inside, which are hydrogen bonded, but not entirely. There are gaps where this is not so. And this is a blow-up of the of this model. So he also has the Levine sugar phosphate backbone, and this is one of the bases here. This is a blow-up of this region here. And this, well, that was in 1948, and it's not correct, of course, not completely correct, because it's got gaps in the chain. But if you look at modern textbooks in microbiology, for example, you'll see structures not too dissimilar from Creeth's structure. This is, for example, replication of bacteriophage mu. So you can see regions of unpaired bases here. So Creeth wasn't to know this all those years ago, that unwittingly he'd produced a structure which was appearing in microbiology textbooks. Let's take a closer look then at the Creeth model. So we just turned it 90 degrees so we can compare it with the Watson and Crick structure. So here we have the comparable models, and both have the, as I said, the sugar phosphates on the outside and bases on the inside, which are base paired. But this has got the gaps, and this hasn't. And this also is missing the double helix. Right. Now, and this is a model that we produced, actually. Couldn't resist this. Sorry about this. We got a ball and stick model. It was designed for making a DNA, but we didn't quite follow the instructions for producing the DNA model they gave. We followed our own instructions, and this is what we came up with. And did something else. This is where the slide rule comes in. It's very, very handy. And Watson's seen this, and he's absolutely happy with this. He's got no issues. I'm sure he had a chuckle as well. But what we've done, we published this paper last year in Biochemical Society Transactions. We've done a little recalculation of the Creeth data from his thesis using theory which he didn't have access to, but we have now. So basically we corrected for the the shear effects on the viscosity to give a zero shear, relative viscosity. And we looked and see that the values he got for the relative viscosity, which was reinterpreted in terms of this parameter here called the intrinsic viscosity, could possibly fit a two-chain model. He had a broken chain because he thought the viscosity drop was so much that there had to be these breaks in the chain. But we doubted this, so we did the calculations, and using these equations, the Solomon-Slayota and the Mark-Howing-Kuhn-Sakurada equation, assuming the molecule was rod-shaped, or the original DNA molecule was rod-shaped, individual chains could be more flexible. And we worked out that a halving of the molecular weight, just halving the molecular weight on secession of the hydrogen bonds, gave a value which wasn't that too far away from the observed value. So a two-chain model intact isn't inconsistent with the original Creeth data. This is not Creeth helix. This is one that we did and published in this paper last year. So here we go. Right, now, so we've answered the question, well, perhaps Creeth, if he'd had access to more modern theory, might have come up with the intact two-chain model. Then there's the issue of the helix. And in 1947, this is before Gulland died, which was in October of that year, Gulland was at this meeting in Cold Spring Harbor in New York on a symposium of nucleic acids and nucleoproteins, and he gave a presentation with the titration data, the purity data, and the Creeth data. And afterwards, he met Pollister. Pollister was the guy who came up with this spectrophotometer for looking at or quantifying DNA in cells, and coming up with this idea that it was the DNA that held the genetic code. So he suggested that there was a possible helical structure on the basis that large chromosomes often appear to consist of helices and helices, and could this be replicated at the molecular level with the DNA? It was a guess. It wasn't based on any data, but it was just a guess, an informed guess, based on how nature tended to coil up large macromolecular superstructures. And also he suggested that the loss of viscosity of DNA solutions after treatment with high and low pH, there was this compact helix form. So helices were being suggested. So Gulland would have gone back to Nottingham with this idea, and what could be done next? Well, he knew of Asprey's work, Belden Asprey's work at Leeds, and knew there are problems of not having good quality DNA, which he had. Then one would have thought that he might have, because Leeds and Nottingham were not that far away, might have made contact and given these samples to Asprey to do further X-ray diffraction methods, and maybe come up with something of high quality like Rosalind Franklin and Raymond Gosling did. However, tragedy struck, and this was extremely sad. I mean, the DNA story is full of tragedies as well as great science. We all know about Rosalind Franklin and the fact that she couldn't get a Nobel Prize because she basically died of cancer, and that was just very, very sad. And the same with Gulland, you know, to get involved in this train crash. So Gulland was involved in all this lot here. So that was, and that basically proved the end of the Nottingham team. Jordan, what happened to him? Well, he stayed in Nottingham for a while. He acquired his own ultracentrifuge, because Beckman Instruments had produced a brand new centrifuge which did take into account the discovery of electricity with the old Beckman Model E. And this is the rotor actually from the Model E. We actually had 3 of these in our lab at Nottingham. This wasn't his, but Jordan set up. And then in 1953, he got the offer to go to Australia, to Adelaide. He called a meeting of his group and told him he was going to Adelaide. And nobody knew what that was, apart from the cricketers. They knew what that was. So, and he took half the group with him. And he became professor, the Angus Professor of Physical and Inorganic Chemistry there, made a big success. And in 1981, the new chemistry building was named after him, the Jordan Laboratories, which was nice because sadly Jordan died the year afterwards, in 1982, but at least he died with the knowledge that he had this department named after him. Creeth, what happened to him? This is a great photograph. This was taken in the old chemistry labs in the Trent building. You can see he's got some sort of vernier caliper there, doing some precision measurement, wearing a tie, as they did in laboratories in those days. Well, Creeth, he moved to London, the Courtauld Institute, then he moved to Wisconsin in the States, then ended up in Adelaide with Jordan, where he had 2 PhD students of his own, and one of them became good friends of ours, Don Windsor. Professor Don Windsor now is in his 80s. He's professor of the University of Queensland. He was Creeth's first PhD student. I was Creeth's last postdoc. So Creeth had went from Adelaide then to Lister Institute in London. When that closed, he ended up at the University of Bristol in the Department of Medicine Laboratories, which was allied to the biochemistry department. And he had the misfortune of having me as his postdoc. And yet again, as one of these ultracentrifuges, these things look like battleships. Now they look like washing machines. It's sad, really. We've got 3 of these in our lab. So they call our lab the Nottingham 3 washing machines, the Nottingham laundrette. That's right. But so this was back in those days. In fact, there's a bit of irony here because after I left Creeth, I was working on substances called mucin glycoproteins while I was with him. I moved to the colloid science part of the biochemistry department in Cambridge, and he applied to them after he left Nottingham for postdoc, but didn't get it, and ended up going to the Courtauld Institute instead. And there's me that got this postdoc position there, which was right next to the old MRC labs of Watson and Crick. So that was the first irony. There's another one as well, which I'll mention at the end. So after Bristol, Mike deservedly retired after a long and illustrious career. While he was in Wisconsin, he met Pat, and he was at Pat right up until his death in 2010. And I had the great honour of giving his eulogy at his funeral in Shrewsbury, and that was very, very, very moving. But Creeth was, I think this reflected Gulland as well, and Jordan, in terms of the meticulousness towards the science. You know, that's why they got this very high pure DNA, because every detail was adhered to. Nothing was left to chance. And he even made us, when we were doing these centuries experiments, when we were handling these ropes, we had to wear these silk gloves for handling these things, because he didn't trust the grubbiness of our fingers. So wherever you are now, Mike, we forgive you. We forgive you for that. So he was greatly missed. Actually, when I was with Creeth as a postdoc, that's when he told us the story of the DNA and what he was doing at Nottingham. So it's another irony that we end up back in Nottingham. But 18 months ago we had a meeting here at Nottingham because it marked the 70th anniversary, 2017, of the publication of those 3 papers in the Journal of the Chemical Society. We had a big meeting of the Biochemical Society and Royal Society of Chemistry. There's about 140, 150 people here, top people coming, talking about DNA and hydrogen bonds. And there was a plaque that was unveiled in the front of the Trent building by Pat Creeth. So Pat and the Creeth family were there in force. We had a nice dinner in the Orchard restaurant afterwards. And that was nice. It seemed that we put the record straight there, and that these people had been appropriately honoured for what was a major discovery. And now the final irony. This was we're trying to track down the where in the Trent building the labs were. And I'm good friends with the English department here at Nottingham. They're also based in the Trent building. And I was having a cup of tea with Professor Judith Jesh and Dr. Christina Lee in the Portland building after a book launch of one of Judith's books. She's an expert, the country's leading expert in Viking studies. So it was after the launch of one of Judith's books on Vikings, and I talked about the DNA here at Nottingham and how the labs used to be here. And I thought it was in the Portland building, not Trent building. And then they corrected me. They said, actually, Steve, the Portland building wasn't built until 1950, 53, 54. So too late. It was the Trent building. So that's interesting. So the question was, where in the Trent building were the old nucleic acid laboratories? So then I asked Martin Polyakov, who's been here a long time, if his colleagues in chemistry might know. And then we came into contact with Professor Stephen Warwick, who used to be Professor of Chemistry here in the 1950s, is now into his 90s. He identified where it was. And so here we are. This is after the help of Christina, Judith, and Stephen. Here we are in the part of Trent building. The picture taken by either Judith or Christina, I can't remember. But the other irony is we're actually standing directly above the English department and directly above Judith Jesh's office. And the reason why that's quite amusing is because, although my main work is in hydrodynamics, I've done quite a bit of work on population genetics with the University of Leicester and University College London, looking for evidence of Viking genes, linking Y chromosomal DNA with surnames, male surnames, old male surnames in the north west region. And this paper was published in 2008, and there's Judith's name there. That's Mark Jobling, who's Professor of Genetics at Leicester. Also Turi King. You know, Turi is the scientist who did the DNA on Richard III, the guy under the car park. So I thought that was quite a strange twist. And Judith said she'd always wondered what this gas tank was right outside her office. And that's the last remaining thing from the old nucleic acid laboratory. So it couldn't have been scripted better, really. Anyway, that's it. Many thanks to all these people who helped me put this talk together. It's been fun and also quite sad, going back into the past, learning about Gulland, and we knew about Rosalind Franklin and things. So some sadness, but some happiness to realise just what role we played here in Nottingham in the DNA story. And in fact, in the latest version of Watson's double helix book, it gives full acknowledgement of the Nottingham contribution. You've got photographs of Gulland, Creeth and Jordan, and details about the train crash and things. Now, these models were too fragile to take up. We tried, the bits started falling off, so we thought that wasn't a good idea. But if you want to see these beautiful things, then come down to us at the Sutton Bonington campus on the 901 bus, which is a free bus which links we had one student once who was trying to get to Jubilee campus and caught our bus by mistake and asked the driver to turn back, which is rather sad. And when he got to Sutton Bonington, he realised that SB stands for two things. One is Sutton Bonington, and the other is... What? That's not what I told you. Something beautiful, or something brilliant. And perhaps the only sad thing is, because all these centrifuges have come back to Nottingham now, and we're actually at SB and not the chemistry department. So maybe the chemistry department can move on block down to us at Sutton Bonington, or maybe we can all move back to the Trent building. I doubt it very much. Time has gone on since then. So, yeah, with that, I'll stop. Thank you.